What's old is new again. That's a phrase that's been applied to everything from fashion to music. But the same is also true about meteorology. A research group at Penn State is applying tried and true data from weather radars like these that have been around for over 3 decades to tell us something new about the atmosphere.
It's just trying to use data that we already have access to that's already stored to do something that has never been done before and collect these observations at such fine timescales and at all these different locations. It was really kind of mind-blowing to be a part of.
A network of 160 weather radars across the U.S. scan continuously every 5 to 10 minutes to detect everything from precipitation to tornadoes. But a team at Penn State has found a new application for the data that these radars collect. It turns out they can tell us something about what is called the CBL.
Well, the CBL is the convective boundary layer, so let's unpack that. First, the boundary layer. So that's the layer of air that's in contact with the Earth's surface and responds to changes in the Earth's surface fairly quickly, so within like an hour. So you can think about basically as, if you're spending the day outside, right? You go out in the morning and it's kind of cool. The sun rises, you can feel the sun on your body and it warms you up, but it's also warming up the Earth's surface. At some point, the Earth's surface starts to warm the air as well, and that air then mixes upwards, and it starts to warm the layer of the atmosphere that's in contact with the Earth's surface. So the daytime portion of that boundary layer is called the convective boundary layer because there's all this vertical mixing that's going on, and oftentimes that ends up being fairly turbulent.
There are many reasons why the CBL is important to us and life on the planet.
Well, it influences a lot of things that can affect human health, air quality and pollution, the spread of wildfires. The concentration of that smoke is really closely tied to the convective boundary layer and the processes that are going on.
The convective boundary layer really sets the stage for what can happen in the atmosphere later in the day. For example, if conditions are right in the boundary layer, we can get thunderstorms to happen.
Despite the fact that the CBL is important to health and weather forecasting, there are still limitations in our capabilities to routinely detect the depth and structure. This observation gap has real-world implications for understanding and forecasting the CBL.
It's really difficult to model, and it's one of the things that we're studying in this project, as well as our observations of the convective boundary layer, particularly my focus, convective boundary layer height, are not very well refined. We don't have a lot of resources for getting those observations.
So we typically observe it by launching weather balloons. Well, we do those twice a day over the United States at 97 locations. But that's not a whole lot of information. We have this layer that grows to very deep depths during the daytime and then is very shallow at night. So it has this distinct daytime cycle that we observe twice a day. And so our research is basically trying to use the weather radars that we have across the United States to actually observe boundary layer depth, how this layer evolves over time, when it deepens quickly, when it deepens more slowly, what leads to that.
With those motivations, the team built upon existing research to come up with a method to fill in the data gaps between weather balloon measurements using weather radar observations. But they first needed to provide convincing evidence that the radars are up to the job. To do this, the team launched small weather balloons called windsondes to confirm that the signal they were seeing from the weather radars correlated with the top of the boundary layer.
The instrument that I showed you that we used, it looks like a little styrofoam cup, like something you'd get with like a kid's meal at a fast food restaurant. It's made of styrofoam so that it insulates the electronics, because when you get really high up in the atmosphere, it gets really cold and would damage the electronics and prevent us from receiving our data.
Yeah, so we're looking for a day, and we've got some sunlight coming in, it's warming up the ground. And then we check the radar data to see that we have a signal that we want to look for. Most of these days are going to be sunny, maybe partly cloudy with some shallow cumulus clouds, but days we don't want to look at is when it's raining or it's cloudy or cold.
While ascending up to 6,000 feet in the atmosphere, the balloons send back data that gives a breakdown of the boundary layer.
The things we get would be wind speed, direction, temperature, humidity, virtual temperature, potential temperature, dew points, and relative humidity.
And from that, we can basically diagnose the depth of the boundary layer from that profile of variables. And then we compare it to what we see with the radar and see how well those two agree. And what we found is that no matter when we launch it during the daytime, we get very good agreement between what the weather balloon sees and what the radar is telling us. And so it confirms this idea that the radar can indeed see the top of the boundary layer at any time during the daytime.
The data gathered by the team has confirmed that weather radars provide information on the CBL and could be very useful for operational forecasting applications, getting the most out of our nation's weather radar network.
I feel like it definitely points in the direction that this could be a very successful automated algorithm for detecting the convective boundary layer height, which is something that's never been done before.
In operations, once we get this to where it becomes more routine, that information on the boundary layer depth could actually be brought into a computer model that forecasts the weather and improve those predictions. It could be used by operational forecasters just to know how deep that boundary layer is. For example, there still are locations in the United States where air pollution can be a problem because the air gets trapped, particularly in like mountain valleys. And so in essence, if they could track with their radar how deep that boundary layer is, that might actually have a better idea of, is it going to get deep enough that this air quality is going to subside because the air will mix in and move over the mountains, or is it going to be stuck in the valley for another day and they really have to worry about the quality of the air that people are breathing.
While the research has shown that weather radars can be used for more than just observing precipitation, radar observations of the CBL can be obscured by storms and other atmospheric phenomena.
But there are days, in essence, when the signals we see just don't present themselves. They're too weak or they're overwhelmed by other things. And so that gets complicated. And so there are days where we're looking for the signal and it's just not there. But those days, thankfully, are not the majority. The majority are days where we do see this signal, where it does appear very nicely, and we can make use of it.
The takeaway is there's still a lot that we have left to learn, even though we've had really nice advances in the field over the past couple of decades. There's always research that needs to be done in improving our understanding of the atmosphere.
For Weather World, I'm Rob Leidick.